Yeah, so the first line of code you see here, which is class equals to the class or class and then linear regression. This is simply a class method. That's what you normally use when you want to define you define something like a class in a Python environment. But before that, the entire code I have here on linear regression is simply a code that defines the simple implementation of the linear regression model. And what I use to optimize the parameters in the model is simply the gradient descent algorithm that we spoke about last week. And also, I want to also stress on the fact that this is simply a supervised machine learning algorithm, which normally use this idea of predicting a continuous outcome variables. That is for the linear regression algorithm. The case where we predict a categorical variable is when we have the logistic regression model, and I think that's what we go into right after this session. Yes, so the the df init function, what you actually see there is simply a method constructor. It is called when an object of the class is initiated. So simply it's what I have there, the solve dot parameter equal to an empty dictionary would be used later. So actually define this thing because I want to fill this particular dictionary with the model parameters, which are the slope and then the intercept. And then define a different function called the forward propagation. And and this whole idea of the algorithm, there's something we call the forward propagation and then the backward propagation. Forward propagation simply means you want to um, take some initial weight and initial parameters and then propagate it throughout the network and produce an outcome. So the case where you want the algorithm to learn, you want the algorithm to learn and to be able to generalize and make prediction, that is when the backward propagation comes in. So it is an idea that updates the model parameters such as the weight, the biases, and other essential parameters in machine learning algorithm. So the function you see here, which is so the function you see here, which is def forward propagation into bracket solve train input, is simply a function um, i- that have been initialized to simply perform the prediction phase of this model. So what it does is that it multiplies the input data with the parameters, which are the slope and then the intercept. So the first one is the first variable that I define here is simply the slope, and which is m is equal to solve the parameter, and then um, the second one is simply the what I we we spoke about last week as the intercept. Yeah. So and all these things that I have here are simply mathematical models. So the predictions is equal to NP multiply M comma train input plus C. So M is simply the slope, and then train dot input simply the X values. And this is simply a linear function, which we saw here, like we saw on Wednesday. So I'm not doing anything extremely different from what you have here. It's simply the same model that we looked at last week. So prediction equals to, and because we are dealing with a numpy array or yes, and you want to use the function multiply in NumPy. So that's why we use this particular um, way to write our model in Python. There's also a different way to go about it. So if you know how to do your own multiplication and then write your own function in Python, then that's fine. I think you can go with that. So NP multiply, then you pass your um, the slope, is equal to mx plus c. So that is exactly what we have here. So your slope and then the number of inputs that we have, simply the weights that we have in the network, and then plus the intercept or the bias. And the bias, I think I've explained the relevance of the bias. Then now right after that, what you have to do is to return the value of the predicted, the value of the prediction. Then the second function simply compute the cost function that we looked at last week, which is simply the summation of the predicted and the difference between the predicted and then the actual values in the actual data point, and this is squared. I hope you can recall from what we did last week. So that's exactly what we have here, and this is nothing but the cost function. So after that, then we return the value of the cost function. Then once we are done with the forward propagation, which is a way of initializing some model parameters and then propagate it throughout the model, the next aspect is when we want the model to actually learn from the data set and be able to generalize on a new data set that it hasn't seen before. So this is where the backward propagation comes in. Again, we define a function. So this function will take in several arguments. The first one is the input function, and then the output, which is the target or the response of the dependent variable. And then in this case, watch out, we are also passing in the predictions. We are passing the prediction because the propagation is going to the backward propagation will use the prediction that is the predicted values that we have, and then check whether these predicted values we have are feasible or not. Then based on that, it will be able to check and then update it and keep updating it, tweaking the values until the right value um, is achieved to maximize the model's accuracy. Yes, so that is for this particular one. And then, this is simply based on the mean squared error. I think someone raised something like that. Why the mean squared error is different from what you are using here or something like that. And I did explain that. So it's simply the average square difference between the predicted and then the actual output. And this is used to measure how well the model is performing. So based on that, we can know that the model is performing well or it isn't performing well. So right after that, then the next one is the backward propagation method, which is simply the derivative of the cost function. So if you can recall, with respect to the model parameters, and I think I demonstrated how to take the derivative of the cost function last week. So that idea, with that idea in mind, what we are and the objective of that or the aim is to use that to update the model parameters in a direction that minimizes the cost function. Yeah, so that is essentially what this line of code is doing. So the derivative of the first one with respect to the model parameter to the theta naught. If you remember, it's supposed to be theta naught, but in this case, I'm using m and c, and then this one also represents the second derivative. So in all, we just print out the derivative of the respective model parameters, and these derivatives are supposed to help us minimize the cost function. Yes, and then right after that, you recall that there was one last equation that we had down there, which is after getting the model parameter that minimizes the cost function, you want to take this parameter and subtract it. Uh, take this parameter and then subtract the learning rate and then derivative of the new function the new value that we get from the old um, the old model parameter. So that is a way the whole idea about updating the model parameter is written in this function. So this function is simply written to update the parameters in the network. So remember, you take the old one and then the learning rate and then the derivative of the the new as in whatever we calculated here, you take the derivative of that, and then you do your computation, and then you get the new model parameter. So essentially, that is what this particular code is doing over here. Now we are done with all the model algorithms. I mean, building the necessary mathematical models. So the next one is to train the algorithm, take a data set and do the training, and then the last one to would be the last but one will be the texting. And once we do the texting, then it means that the last aspect of the whole process is to check for the accuracy of the model using any of the metrics that are available, or yeah, any of the metrics that are available, or any of the feasible metrics. Yeah, so this train function that we this whole train function that we see here from I think it starts from here. Yeah, so this whole train function that we have here is very simple. It's doing nothing, but it's simply the main function that trains the model. So it first initializes the model parameters randomly. So that's what I yes. So it initializes the model parameters randomly, and then it then performs forward propagation, calculates the cost, and then perform backward propagation, and then update the model parameters for a specified number of iterations. So the learning rate is also passed to control the size of the parameters. The process of it being updated. I told you last week that the learning rate is simply there to determine the step size of the the how do you call it, the gradient descent algorithm. So the cost after each iteration is simply stored in the list lost and then printed out. So that's essentially what I have over here. So the whole thing is stored here, and then it's finally being printed out and the end of the whole process. So the three stages. The first one is you building the algorithm, and then the second one is you simply coming up with a mathematical model and writing it in the form of Python code that computes the forward and then the backward propagation. And then the last one is you training the algorithm and then being able to test it on a new data set that it hasn't seen before. So essentially, that's what the codes are doing. So this simply initialize. So np dot random uniform, you're just initializing new parameters. So the new parameters, the weight and then the intercept, you want to initialize the model parameters, and then after that you want to store um, these outputs, which simply the learning rate, to which determine the size of the gradient descent algorithm, and then which the cost function actually utilizes in the process of iteration. This whole process, the process of iteration and all that are being, the iterative processes are stored in the function, the variable that have been defined as uh, lost equals to the empty list that I have here. Yeah, so it means that we are done. So the next thing is to just do loop through the entire data set. So prediction is equal to software. Then you pick the forward propagation function, which we already built, which is this one, this forward propagation function. Then what you do is to uh, pass in your training input. Then it does the training. Then right after that, you take your cost function again, and then that is what you use to um, you pass in your train input again. Then it goes in and then calculates the model parameters that will maximize the model's performance and then minimize the the cost function and all that. That is minimizes the loss. Yeah, so that's essentially what this saying. This code here is simply just by the way. So what it's doing is that is just keeping track of each iteration. So after every iteration, it keeps track of how the the model, the loss function is reducing. So it takes the loss function, then this simply points out the loss at every iterative step. Yeah, so the backward propagation. So we need to update the weights in the network. So this taking three simple arguments: the train input, and then the output that you are getting, and then the prediction. So it takes that to update the weights in the network. Yeah, so that's basically what it's doing, and that's the function, and then it takes in this route, and then right after that, the next one function also utilizes it with the learning rate and all that, so it determines the step size and all that. So finally updates the model parameters, and then it picks the feasible one, the right one that would be necessary in terms of minimizing the cost function. Then once we are done with that, we want to print out these parameters that minimizes the cost function, and then the loss associated with it. So if you have the notebook, you can just run the whole thing. So you run the first one, second one, you run it.
Hi,
Then
please. Sorry. Just hello.
yes, I'm listening.
Me, I'm getting error where you are running the notebook just in the first one where you use the CSV file. Can you please go to the,
You, you mean this, please?
yeah. Okay,
Yeah,
yours is
do.
notebook data collapse, but mine is I loaded the data into my repository, my laptop, and then I pick it from there, but it still is not running.
Did you load the data inside your Google Drive, or it's on your local machine?
I also put it on my Google Drive and my local machine, but
So
usually
which one are you using now? Are you working from the Google Drive, or you are working from your local machine?
I tested both of them; they are not working.
So if you are working from your drive, you simply go to this particular icon that you see here. Then you click on it. Then your drive would be mounted. Once you mount your drive, you have to go to where the data set is. So in my case, the data set is simply inside Colab Notebook, and you realize that I've created a folder for it. Here I have the arrays data set here. So what you're supposed to do is to click on it, and then you copy the path. Once you copy the path, you come and paste the path right here. You paste the path here, and then as soon as you run this cell, you should be able to figure out the path, and then uh, import the data set right from your Google Drive. Did you do that?
Yes, but it's still not. See, mine is I think is not imported in the same place.
So just tell me
In mine,
the processes that you use. How did you go about it?
so usually I have two options. As I put it inside my drive, and then let me try to see if I can re-upload it again, maybe. Uh,
So once you upload the data set into your drive, the next thing you're supposed to do is to locate where the data set is within your drive, and then you copy the path. Just copy the path and then come and paste it inside the cell right here. And if you run it, it should be able to run perfectly without errors.
uh, yeah, let me.
So I think you can
I'm
try
going to
that.
test that. Yeah, I'm going to test that. I re-uploaded into a different part, different place. Let me see if
Okay.
that's going to work. Yeah. See, just the content. I think it should run this time around. Not this. It's still not running, Prince. It's still not.
So what is the
It says no such. I loaded into. See, what I did was I loaded into a folder called sample data where I put some stuff. Maybe I need to remove it from that.
Mhm.
Uh, but it's not going through. Nothing is.
You mean it's still not working?
No.
Can you
So
try your local machine?
Yeah, it is in my local machine. Usually I
So
copy
so
from
the
my.
local machine, I think if yeah, so if you open Jupyter Notebook, just go to File and then open it from the folder in which your data is. I think that would be very simple.
Yeah, but you see the file is there, right? Normally what we do is you just copy the path as a even from your machine. You just open the folder, you copy the path as a copy, and then you paste it, and you change the backslash to forward slash, and then it run. Or you upload it into your drive, and then you take it from there. But both of them are not going through. Uh, but I'm using collapse because it's supposed to work. I even went and created a separate folder into my own drive to also test it and copy, but it's still not running for some other reason. It's not going through.
Which means that you've actually utilized almost all the options that you have and it's still not working, right?
really don't know how to. I'm coming. Give me something. Okay. So let me go speaking again. So what I'm saying is that the first thing you're supposed to do.
Let me figure out a plan B, maybe. So
The first thing you're supposed to do, can you hear me? The first thing
yes,
you're supposed to do is to first of all go to your drive and then upload the data sets.
yes, that's
Then
what I
once,
did.
yes, so you've done that.
Yeah.
Now, when you open Google Colab, what you're supposed to do first of all is to go here and then mount the drive. If the drive is not mounted and you try
Right.
importing the file, it not work. So you mount the drive. So you click on this link and then
Yeah,
this
you click so that that
comes
arrow
to come.
can move. I did that. So it's no
So
longer there.
let's
It,
invoke
there is
access
no,
to a new runtime.
yeah, it used to
Then,
that way. I'm not sure. Maybe I might need to restart my laptop or for some other reason. I
no,
don't
it's
know.
not about restarting your laptop. You are not really using your local machine. You are using Google Server, which is the Google Colab. So it's not any, it doesn't have anything to do with your machine. I think it is just some technical thing that has to be fixed. So simply, I think you are just not doing the process that they are using to import the data isn't right. So that's what you're supposed to check out. What did you say the feedback was?
Sorry. Oh yeah, let me go back to the feedback because I was using Colab, but um
And then he said it says unable to reach file or something.
sorry, just a second.
Uh, can he not share his screen?
Yeah, I can.
Are you able to share your screen?
Yeah, I can share my screen. So
We
let
don't
me.
have much time. That's the problem. I'm supposed to
Uh,
finish this
yeah. Prince is supposed to finish.
and
Okay, go. I will
assemble.
follow. I will follow up. I will follow up
So
and
probably we can, yes,
yeah.
because right after today, I don't have any other session again to complete. So I just have to make sure I finish whatever I'm supposed to to work on.
All right,
Yeah.
Prince. As he's looking for it, so after being able to develop a class or a module like this, um, how do you use if you are able to train your data and predict, um, what then do you use the what you have got for? I mean, being able to you have been able to train your data, you are able to predict, you see that it works fine, or there's some accuracy or something. What
Yes.
again is it the application of it? That's what I mean.
Yes, it means that the model can now be used. You can now use the model on real for solving real world problems. For instance, the the models that are able to predict weather conditions and tell you that it will rain around this time, it will rain around in this particular day, and all that. These are models that have been trained on historical data set and they've tested it with data set that it hasn't seen before. So now the model can now be trusted. So you can now integrate the model in some systems that will be able to read or collect data sets from real world from collect real time data set and then at the same time implement um, fit these models on this real time data set and then it will be able to do predictions. Another example is the thermometers that we normally use in our labs and other devices that are able to check whether someone has meningitis or not, someone has diabetes or not. Yeah, so in one of your projects, I think some of the groups will be working on meningitis, other people will be working on diabetes and all that. So these are all models that have already been trained. So once the model is trained and it is being tested on a data set that it hasn't seen before, we can now integrate these models in devices which can collect features and real-time data set, and then at the same time do predictions. I hope that answers your question.
Oh, okay. So fine. Now I see that this is a linear model. So do we have other models which are nonlinear and stuff? So that
Yes, yes,
if
there's a lot of
the data is not um the pattern in the data is not linear or something, maybe it doesn't work well with the linear model.
exactly. So there are a lot of non-linear models. There are even clustering models. So logistic regression is a non-linear model. So we look at that right after the linear regression. The reason why the logistic regression um, came into being is because the linear regression couldn't distinguish between data points that are non-linear. So the logistic regression is simply some kind of modification or a generalization of the linear regression to be able to distinguish between data points that are nonlinear. Yes, and to be able to also categorize between categorical data, whilst the linear regression is simply focused on continuous data points. So yes, the support vector machine, the random forest, the XGBoost, almost all the boosting algorithms, as well as the neural networks, the deep neural network that we have, they are all algorithms that are based on this idea of being able to distinguish between data points that are nonlinear in nature. And in real life, almost all the problems we solve are nonlinear. That is why it is essential for us to depend on nonlinear algorithms to solve this problem that we have in our everyday life. Yes, so there are a lot of algorithms. There's so many algorithms that are um, non-linear based.
Okay, so like this random forest SVC and those things like SVM, um do you have to code it again like this? Because I understand they are in, you can import some of them in Python, but you have to code them, or maybe you need to tweak some of the things. That's why you need to code them, because I can see you are using the class and those things, and I don't know whether that have been captured in these lessons.
Exactly. So that's a very good question. So the motivation for this particular study is to expose you to some of the mathematics and then the programming aspect of the algorithm that will be important. If you are in industry, you are going to do some kind of analysis and prediction. You don't need these ones. But then it is necessary for you to know some of the motivations and the mathematics behind most of the algorithms out there. So if you are working in industry, what you are supposed to do, if you are working with these classical machine learning algorithms that you have, you just have to know how to work with sklearn, that is scikit-learn, and just import this algorithm from scikit-learn and then use them for your predictions and your analysis and all that. If you are dealing with neural network, you simply have to know how to work with TensorFlow and download or import these libraries from TensorFlow and use them for analysis. And there are a lot of libraries, there are a lot of platforms, and there's PyTorch, there's sklearn, there's the TensorFlow. There are different libraries and then platform where you can import these libraries and then use them for analysis. So I just want you to know that the way these algorithms work is not based on magic or this idea of a black box. So I just wanted you to have a fair idea of the mathematics behind these algorithms, how it was actually coded from scratch, and then something like a motivation for you to know that, oh, okay, this is how it works. So you get it.
Oh, okay. That's great. Because I've tried to understand these things, but it seems it's taking time. The cell
Yeah,
parameters and those things. Yeah.
yeah. So one thing about programming, if you really want to do data science, you really want to go into industry or in academia and do advanced data science and all that, you have to know how to know these things by heart. For instance, if you go into industries, there are some data sets that when you receive right now, you would have to know how to code some things from scratch. Yes, you are not always going to import libraries from sklearn or TensorFlow. You have to be able, as a machine learning engineer, you have to know how to code some things from scratch. Yes, these activation functions and all that. You can have a model or an algorithm that works, but then you realize that based on the problem that you are particular problem that you want to solve, the activation function that a particular type or an algorithm utilizes couldn't be feasible to solve your problem. So in this case, you would use the algorithm, all right, but you have to know how to take the values and then code something from scratch and integrate them into the library to be able to solve the problem at hand. Yeah, so in as much as it is essential for you to know the processes and how to code them from scratch, I think it's also a motivation for you to um, develop some love for programming so that in the future, if you are stuck somewhere, you'll be able to rigorously code some things from scratch. So the book I shared with you, the two books I shared with you, they are very good book. And in terms of how to program in Python from scratch and all that, it will be extremely useful. So I encourage you to make use of them.
All right. Thank you very much. I think this is very helpful.
Hi, Prince, before you go, I think the code that you have on your file is
Yes.
almost not the same as what I have. It's like you're using a different file when we have the same naming.
Yes, I updated the files to this one. I've spoken about this ones already, which simply drops the missing values in the data sets. And then reshaping the data set. I've explained those terms again already. I think so. As you realize from is it okay? This particular line of code that I have here, that's exactly what it's doing here. So after every iteration, it prints out the loss, and you can see that the loss keeps reducing. So in this particular case, we use only 20 iterations. So you can use about 100 iteration and then look at the dynamics and how it is reducing. So for 100 iteration, the function, the loss, um, the value for the loss keeps reducing. And that tells you that the model is how the model is proven. Now, this line of code simply also prints the linear function that we coded from the beginning, as well as the data point and how it's been able to distinguish between the data points. So that's exactly what this line. So it gets a visualization of how it looks like. Yes. So I encourage you to go through these lines of code again. The thing about programming is practice, practice, practice. So you keep practicing, you find different things, you read more, a lot of things, and you know how to go about one particular um, problem. I mean, how to solve a particular problem. So I encourage you, even though I've taken you through, I encourage you to make time and then go through them yourself. let's see if I can share some links to it here. All right, so before I forget, let me send you some links before I proceed with them. Yes, if you have a question, please go ahead and ask.
Yes, I have a question. I think I'm having an error.
Have we tried the new
On
notebook? Yes.
yes, it's giving the same error when trying to. Is it on the class linear regression part? Just from the valid data set and labels.
Valid
Then
data set.
yes, there's an error message. I'm getting.
Yeah.
I mean, where exactly? I don't know.
Is it line
Is it this place?
line 8? Yes, that one. Valid data set and labels. When you run that,
I don't see valid data sets.
the previous one, test input and test output.
You mean this place?
Yes.
I think you just have to rerun again.
I think it has to do with the data sets. Have you been able to run this line?
Yes, I have.
And did you get this data frame?
Yes, I did.
Run the
Did you
next
drop?
one. I'm sure you
Did
jumped.
you drop?
You jumped a step.
Did you jump? Did you drop the missing values?
Yes, I did.
So what's the error
So
message you're getting? Parameter not found.
Uh, it's saying
please try running it.
cannot
Please
reshape
try running it.
array of size 200 into shape
It's
199.
because of the data set. Please run from the beginning again.
Okay.
Run from here. Let me see here now. Let me know if the problems still persist.
Okay, I think it's fine.
It's fine. Okay.
Yes. But on the other part, on the linear
Which part?
regression part,
Yes.
given an error.
My God.
What is the error message?
Saying name linear regression is not defined.
Yeah, you
Yeah,
have
so
to
it means
run
that you've not run
it.
the function.
Yeah, you jumped it. You need to run it. You jump some steps.
Please make sure you don't jump any function, any line
Okay.
of code. Every line of code is very important.
All right, it's fine now.
So let me quickly share some resources with you before I forget. Um, so that's the first one that is based on machine learning from Google. And then I think the last one is simply a paper. So I have a book here, Mathematics, a very good book. So, it's, and for those of you who want to do deep learning as well, you find this useful. And then this is also a GitHub repository where you can find a lot of content. I wish you all the best. Yes, so let's continue. Let me stop sharing this and then logistic function. And this is also called a hypothesis function, and it's giving us this the h theta of x, which is equal to the function g of theta transpose of x. So this function g is simply the sigma function, and it is given as 1 on 1 plus e power negative z. So this is simply a function. So the sigma function is a mathematical function, and that's what we use to map the functions, map the predicted values to the probabilities that we have. So you have particular values in the data set, and then it being able to distinguish the data points in terms of probability distribution. And this whole process is done by what we call the sigma function. So it's a mathematical function. And this mapping function is bounded between 0 and 1. So as I said earlier on, values above the threshold value tends to 1, and values below the threshold value tends to 0. Yes, so last week someone asked a very good question that the cost function in the linear regression doesn't mean that we have other cost function also in other models as well. Yes, so in logistic regression, there's a cost function, and the cost function of the logistic regression is given by this mathematical formulation that we have here. So j of theta equal to this a particular equation. This equation is known as the logistic regression function, or the cost function of the logistic regression algorithm. Yeah, so and the gradient of the cost function is a vector, so of the same length, and it's supposed to be the same length of the modulus parameter. And in this case, the jth element ranges from 0 to all the way to n, and is defined by this particular equation that we have here. So we realize that this gradient looks the same as the linear regression gradient. And so the formula can be the same actually, but in linear regression, they are different. The the hypothesis functions are actually different. So they don't have any, even though they can be similar, and the method of computation is actually different. Yeah, so that is for the linear regression, very simple and short. Do you have any questions in the linear regression? The same process we use for updating the weights, then doing the derivation and all that in order to optimize the model parameters. We use the same processes also for the logistic regression algorithm. Right. So
Hi, Prince. I have a
yes,
question. The cost
yes.
function is only function of theta. Why do you differentiate it with respect to theta j? Because normally, when it's linear, we have the theta j is because j is 1 or 0, as a 0 or 1, because the linear one,
Yes.
which is a linear function. But in this case, the function is not linear, and there is only one theta. Why are we taking theta j again?
Yeah, so this is a prediction that is based on categorical values. Okay, so it is going to do the prediction categorically. That is true or false, yes or no, zero and all, one and all that. So you can see that what we have here is a function that does that. So the whole of this, the first part of the function is the one that computes one categorical variable, and then one minus the whole. So you realize that this whole thing is kind of similar. It just the difference is you taking subtracting it from one. So probability. If you get probability value, then it means that one minus that this particular probability value will give you the other probability, and probability also always sum up to one. So it's because we are dealing with categorical value. This is a very good question, actually. I
And,
hope
and
that answers the question.
Yeah, thanks. And in the previous one, when you have h theta minus y squared, we said that that can be seen as the mean square and so on and so forth. And the difference, we can also understand the difference in terms of cos and so on. But here now,
Yeah.
how do we explain the 1 minus theta and the log in terms of the data? Because you see, if you take h theta of xi minus yi, we can
Mhm.
explain that in terms of the data, right? Because you can say H is the logistic regression, and then YI are the predicted variables, right? Then
Mhm.
XJI are the inputs. But what about the one minus the predicted? So because the predicted are so many, so we take one minus the first one minus the second, and so on and so forth. How do we explain that in terms of simple English, in terms of the data, and with the log function and all this?
I mean, how you can explain? Okay, so let me say this. In the logistic regression algorithm, we are simply dealing with binary classification problems where the dependent variable takes on two possible outcomes. So this possible outcome, as I said, can be 0 or 1 or true or false. So the logistic regression model simply estimates the probability of the positive outcome given by the values of the independent variables that we have. So the independent variables that we have here will simply be the features. And the most commonly used function that you normally use in this logistic regression algorithm is what we have here, and that is the cost function. In physics, people call this equation the cross entropy loss or something, yes, and all that. So the value that I have here, sorry, the equation I have here, the M simply refers to the total number of data points that we have in the data set, or the number of samples. I think I really get. So I don't know whether I'm answering your question, but the cost function in logistic regression simply represents a measure of this discrepancy between the predicted probability and then actual binary outcome in the observed data points. And minimizing this cost function simply allows the logistic regression model to find an optimal parameter. So let me see if I have an image to show. No, no, I can show you an image to clarify this point or what the question that you actually asked.
Because you see, if you look at the h theta of x minus the yi, that is the losses, right? When you summing up all these losses over the entire sample, then that gives the cost. So the cost is just like taking all these losses, adding them to each other. At least then we can explain it in a simple English to anyone to understand. And then say, okay, we take all this, we take all the losses, and then we multiply them with the input variables. Then we add all these losses together, we get the cost. And to differentiate it is okay. We know to differentiate, you get the depending on what you want. Then some take the average.
I don't really get what you're saying. What did you say?
No, it's
Let me
fine. I'm
put
just
the
I'm just trying to put a sense into what. But I think it's okay. Maybe we'll take it to another discussion when we have time.
Oh, okay. So you're fine or you're okay?
Yes, yes, yes. I'm fine.
Okay. So, yeah. So let me check this thing. So if you look at the second part of the notebook, you realize that, and that has to do with the logistic regression model from scratch. Can you all see that? Work is the logistic regression, and also for motivation, I would like to go through these ones as well. Okay, so this is simply the Python code that represents the implementation of the logistic regression, which is a supervised learning algorithm. So again, we define the class instructor that initializes the takes in some input parameters or input arguments such as the learning rate, the number of iterations, the weights, and then the bias. So we set those things to be none. So this will be set again during the fitting process or the fit method. Is Give me a minute. Yeah, so that is for the first line of code. So just define a class environment, and then we have some input agreements. So the learning rate, the number of iterations, and then we initialize some parameters too as well. So we initialize 4 different parameters: the learning rate, the number of iterations, the weight, and then the bias. And we set the bias, and then the bias, and then the weight to be equal to none. And so in the process of fitting the algorithm, this will be redefined again. Yeah, so the next line of code, which is what I have here, um, is a function that is written to fit the data sets, to fit the algorithms to the data set. Sorry. So the fit function that you see here simply starts by getting the number of samples. So the number of samples, mm, the number of samples that we have, and then the number of features and the data set will probably contain from the shape of the input data x. So the weights are then initialized as an array of zeros with a length equal to the length, which is equal to the number of features that we have, and the bias is initialized with 0. So in this case the bias is equal to 0. So the process of building the algorithms or teaching the algorithm to learn this will be updated as the algorithm keeps being as the algorithm starts going through the training process. And then the next line of code, which is the gradient descent algorithm. I think I've said a lot of things about the gradient descent algorithm, which in this case the gradient with respect to the loss and then the weights. Um, sorry, the gradient of the loss with respect to the weight and then the bias is actually calculated with this particular line of code that I have here. And then the weights and the bias are then updated by um, simply subtracting the gradient scaled by the learning rate. So that's exactly what I have in this particular. So I think so. This whole process is we going through all this whole process contains the gradient descent algorithm, and then you update the weight, which I just said. So update the weight of the model. Yes. So that is for the whole of this side of the codes that I have. So I think I've already spoken about the fitting and all that. So the last one, the next one has to do with um, a predict function. So the predict function is simply a function that calculates the predicted class labels for the input data. And the input data defined there is the capital X that we have here. So what it does is that it simply calculates um, the linear model and passes it through the sigmoid function to get the predicted probabilities. So these probabilities are then and the threshold at 0.5. So what I have here is simply the threshold, which is 1 if the threshold is more than 0.5, and then 0 for 0 else. So else, so greater than 0.5, else if it is not greater than 0.5, it should give an output of 0. And then I think I'm done with all that. So that's all. So it means that the whole of this place, you are done building the algorithm, you are done building the model. Now the rest is just testing. So this just imported the classification metric from sklearn. Sorry, the model, the print test plates function from sklearn, and then once we import those important libraries, we can then use and then uh, a data set was also imported from muscular, which is a breast cancer data set. And then so this accuracy function has already been built up there. So define an accuracy function, and the accuracy function simply take the true values and then the predicted values. So I think I took you through the confusion matrix, which outlines how the accuracy is being calculated. So the true value is being equal if the true value is equal to the predicted values, or divided by the number of true values that we have. So the actual value. So we pick all the values that were predicted accurately divided by the total number of actual values that we have, and that gives you the accuracy. So this is just a function that computes the accuracy. So you define the function, and then you pass the data set that you imported from sklearn, and you define your your the features that you have, and then the targets that you have to be equal to that. So the features equal to this bc.data, and then the target will be in this um, variable, saved in this particular variable y. Then the rest of the thing that you are supposed to do is to just pick the regressor that you, the logistic regression that you build, the class function that you build all the way from the side, and then you pass in. Remember, it's taking two arguments. The first one is the learning rate, and then um, the number of iterations. So we set the number of iterations to be equal to 1,000, and then the regressor now will fit the model to the data set that we have. Sorry, and then we do the training from this line of code that we have. Then the next one is the prediction. Yeah, so you can run this, then it runs perfectly, then you just check the accuracy of the best. Yeah, so I think it's pretty simple, and it was quick too. Do you have any questions?
Yeah. I think when
Yes,
you say pretty simple, I think it's so difficult for us. So
really.
I
Sorry
think
about that.
if you go to line number 13,
Line
I'm not
30.
sure. You said the bias to none outside
Yes.
the logistic regression. And then suddenly you set it again inside the logistic regression. When you are defining the function inside, you set it to 0. I'm not sure what's the difference. Why do you do that for the bias at the same time? You initiate it to none, then you initiate it to 0.
Yeah, so from the beginning we don't we set the bias to none, which simply means that we don't want to use it now or utilize it now to do anything. So now that we want to use it in the algorithm to do some computation, then we now initialize it to 0. So if you look at the first line of code, which is this particular line of code that I have here, the bias was simply set to none. Yeah, as I explained earlier on. Yeah, so it is set to none simply because we don't want to use it now. So if you are ready to use, we just initialize it to 0, and then we start using it for our computation.
Okay. And then you see, we are like defining a class for, if we are building a class for the logistic regression.
Yes.
But then just after this class, you are using the linear regression. I'm not sure if I understand. Why are you using the linear regression inside the logistic regression?
The linear regression inside the logistic regression, where exactly?
Yeah, you passed it. Yeah, you see here, when you are doing the prediction, instead of using the logistic, you are using a linear model.
You mean here? Is it
Uh,
this line of code?
Go a bit up. No, I think then it's me who's misunderstood it. Okay, thank you then.
So any other question, guys? Okay, so I think I can quickly go into the decision tree. And please, if you have any other question, feel free to leave it in the chat box, or you can just prompt me. And these are very good questions, and I really appreciate you guys for the great questions. Yes, the last one, I'll try as much as to catch up with time. So yeah, so if you look at the outline carefully from last week, from Wednesday, we had this inside the outline we're supposed to talk about. This ensemble learning, I think ensemble learning in specifically in machine learning. Yeah, so ensemble learning in machine learning is a very interesting technique that involves the idea of combining multiple individual models called the base models or weak learners. So you have some algorithms that are able to predict very well and other algorithms that are very weak. So to create a stronger and more accurate predictive model, the idea behind the ensemble learning is that by combining the prediction of multiple models, the ensemble can overcome limitations and biases of individual models and then make more robust predictions. So this limitation that I'm talking about has to do with overfitting, underfitting, and all that. So in ensemble learning, the base models are simply trained independently. I think we will look at that. And so I I chose two aspects to speak about. The first one is bargain, which is also known as the bootstrap aggregation, and the next one is the boosting. So The last one is simply what we call stacking, and stacking is simply an idea of combining the prediction of different models. Yeah, so how does these models work? So different models may be good at different parts of data. So if the data underfits, then it means that it will not be able to generalize on a new data sets again. And if the model is overfitting, then it means that the model is learning too much from learning too much and distinguishing too much between the data points, and again it wouldn't be able to generalize well on a new data set. So these are individual flaws of algorithm. So the whole idea about the ensemble learning is to combine the prediction, the strengths and weaknesses of these algorithms, and use them in building a new model that will be able to handle these indifferences and give a better prediction. So then it comes to the question. So which model should be combined? So in terms of which models could combine, we need to check for the bias variance analysis. So we check for models that has low variances and then models with higher biases. So a model with that underfit simply means that the the bias in that particular model is high and then the variance is low. So it means that what you're supposed to do is to combine this with a model that has a low bias and then kind of a high variance to handle this particular problem. So the process of reducing the bias in the model is what we call boosting, and then there is process of reducing the variance in model is what we call bagging, and stacking is also this whole idea of combining these two models together to get a very good accuracy is called staking that I explained earlier on. So yes, so bagging is simply a technique where each base model is trained on a randomly sampled subset of the training data with some kind of replacement. So you train the data, then you do some replacement again. That is the whole process of the bagging. And boosting is also different way of handling the bias, which means that the process of reducing the bias in the model. And there are some algorithms that are associated with the bargain. I think a typical example of algorithm that uses the idea of bargain is decision trees and then random forest algorithm. And then when it comes to boosting, we have the other boost, the gradient boosting, and SG boost, and all that. So there are a lot of reasons why ensemble learning is very, very important. So one of the advantages of ensemble learning is over the individual model that we normally use is that it improves the accuracy, the prediction accuracy and generalizations. And it does this by reducing overfitting problems and this bias problem that normally results into models. Yeah, so ensemble methods also are robust in reducing the noises. We study about noises and what noises are, and also they also handle these outliers in dataset, and they are widely used for so many um, stuff. So SG boost, other boost, gradient boosting for boosting, and then decision tree, and then random forest. A typical example of this area of study. So yeah, I'll quickly go over this and then talk about decision trees. Yeah, so decision tree is simply a predictive model that uses the flow chart. You know, the tree that you see, it's kind of has some decision boundaries, and the whole process is based on decision. So it divides data into practice and assign outcome to leaf nodes. So that's simply what. So you have a whole data set. So you have a data set that looks like this, and then what it does is that it cuts the data set into two, and then keeps asking some questions, and then based on that it checks the purity level of this data point, and then it uses that purity level to split the data set. Decision tree is very robust. It's one of the interesting algorithms that have been developed so far in this area of machine learning. Yes, so some important terminologies to take note of. The root node. So the root node is simply the node present at the beginning of the decision tree. So the node that we see here is what we call the root node. And then the decision node is the node that we get by splitting the root nodes. So if you split the root node, all these particular nodes here are simply called the decision node. So this is a decision node, this and is a decision node. And then the leaf node is simply, or the terminal node is simply a particular node that when you get to, you can't split the data set further. So it's kind of the last node in the splitting process. Yeah, so sub tree node, these are simply sub decision trees, and the pruning is simply a way of cutting down some nodes to stop overfitting. So when you realize that the model is trying to overfit, then you have to uh, cut down some nodes to avoid overfitting. So these are some terminologies that you think you should be aware of. Then yeah, so from this data set, a practical way that a decision tree uses to a practical way on how or how a decision tree uses to generalize between data points and all that is based on this particular idea that if you have this particular data point, then so this is a data set or weather information that is based on whether it is sunny, is cloudy, or rainy. So three labels here that we have here, or three target features, target variables that we have in. So sunny, cloudy, and then raining. So you ask a question: is it sunny or is it cloudy? Or so based on how the question is being asked, then you know how to split your data set. Yeah. So now, how can we do uh, prediction, or how what are the methods that the decision tree uses to split the data set? It uses two different methods. The first one is what called the Gini index, which is simply the summation of the probabilities of the classes. So where the the first class is not equal to the probability of the particular class is not equal to the other. So that is for the first one, and then another method that the decision tree uses to do the splitting is what we call the entropy. So the Gini index came in before the entropy also came, which also utilizes the probabilities, but in this case, a log has been introduced. Yeah, so these are fancy mathematical uh, equations that I wouldn't like to talk much about. So, but then I would like you to just know that there are two methods essentially: the Gini index method and then the entropy method. So do you have any question? So I think this too has been very
Oh, yeah, so far,
quick and simple.
so good. We are hanging in there.
Yes, I think it looks like it's kind of difficult to grab, or is it?
Someone sent in the chat saying like it looks like a very complicated. complicated.
It's not really complicated actually. I think as time goes on,
It says it's like meeting operator theory again.
it's like let me check what it is.
Yeah, it's like meeting operator theory again. Yeah, Malama is killing us here. Malama, you said it's like meeting operator theory again. Yeah, but we are hanging in there. We're trying to understand we can, as much as we can grab.
Okay. I have about 20 minutes more. Let me try and slide it. So the last thing that I want to talk about is the decision tree algorithm. Sorry. No, yeah, so this so a way to implement the decision tree algorithm. So I'll try as much as possible to explain each line of code and help you. And then the one was saying that it's kind of confusing or they don't really know how to go about it. So um, this slide, all the codes that I have here is the first line. I don't think I should talk about this libraries already. I think you already know about. So what I have here is simply to import the necessary module that is the collections modules and then the counter and then the numpy library. So this entropy function that I have here simply calculates the entropy of a set of labels y. So the set of labels that I have been passed as an argument called y, which measures the impurities of the input set. So that's exactly what this line of code is doing. And in this case, we are using the entropy, which is the log, the probabilities, using the probabilities and then the log. So that's exactly what I'm having here. So in a um, So remember I told you that we have two ways, the Gini index to measure the impurities, and then the second one is the entropy. Yes, the entropy. So that's what you are using. So in this line of code, you are using the entropy instead of the Gini index. And then the class that I have here called the node is simply a class that simply defines a decision node. So and then decision node, and as well as to define some model variables that will be used. So each node can have a feature and a threshold value to make a decision, and two child nodes. So when splitting the the data set, you can either split to left or split to right. So the splitting is done in two ways. So you split to left or right. So these are just possible ways of doing your splitting, and that's exactly what you are doing here. So define a class, and then you set the features to be none. Again, set all the features to none, and again you when we are about using it, then we initialize and we set them again to the we set them exactly. So right after setting all of them to nine, we define them to be equal the feature, the threshold, the left, and then the right. So this, whatever you see here, is simply a way of defining some variables that we are going to use in the model. In the decision class tree, to exactly that's for the whole of this particular site. So when we come to the next line of code, which is the decision tree class, this is where the actual decision tree algorithm is implemented. So it takes in the minimum sample, which is to the maximum depth. So we are using a maximum depth of 100. So the whole thing is that if you have a data set, you can actually decide the number of depths that you want to go into. Or apart from the number of depths, you can also decide the number of different way to split your data set. But then it's mostly advisable to set the number of depth instead so that it can automatically um, uh, stop when you reach the number of depths that you have. So again, we set the minimum samples to the minimum sample that we have. The maximum depth, we set it to be equal to maximum depth, and then the number of features to be equal to the number of features, and then the number of root to be equal to the number of root nodes that you want to have. So the fit function, right after that, we need to fit the model to the data sets that you have. So the first one, you define the function, and then the function are passing in the features and then the target. So this whole fit method simply trains the decision tree on the input data and the labels by, and then it first determines the number of features to consider when making each decision. So that is if the number of features is not provided. So, and the number of features must be is this length, the length of a particular feature must be the same as the shape of the shape, or that is the first, when you do something like that, it means that you are actually taking the shape. So the first one represents if it will be zero, it simply represents the number of root, and then one represents the number of features. So this number of features simply means the number of um, x dot shape is simply picking the number of features that you have made. If so take the if to be x dot zero, it means that it simply means the number of rows, which means that the length of the data set. So yeah, so right after that we have the predict function, and this predict function simply makes prediction for the set of samples. Now this is the fancy aspect of the decision tree algorithms, the grow tree recursive um, decision tree. So what this does is that it recursively builds the decision tree. So what it does is that it first checks for in decision tree we have what we call the stopping condition. So we need to set first of all when it is supposed to stop and all that. That is when that is the maximum depth that to reach and all that the number of samples that we have. In the number of samples we have, the data sets that we fully utilize, then it means that if you reach a particular condition where the whole thing to break and the splitting will stop. So it means that if any of these conditions are met, then it simply creates a lymph node with the most common class. So remember earlier when I said the leaf node is a node any further decision for splitting, I mean that will be the last node in the algorithm. So that is where this whole um, line of code, that is what this whole line of code is doing. And the topping criteria. So really explain it. Criteria. Then for the information gain, I think I didn't talk about the last. I think there was a last line of code that I was supposed to explain. And so I spoke about the Gini index, the entropy. One last equation that I was supposed to talk about is called the information gain. So what that does that it simply computes the information gain that will result from a splitting. So after doing a particular kind of splitting, then you now know the information that is gained as a result of the splitting. So that's exactly what this particular line of code is doing. And then so the split method simply split the sample along with the feature at a certain threshold. So at a certain threshold values, that's where the splitting takes place. So it takes place at a particular threshold. For instance, if you set a threshold to be um, equal to some number of um, did I set this somewhere? Okay, so the threshold there was set to be none and it's set to a particular threshold. So it means that when you are building them, when you are ready to pass the data set, then you define your own threshold. So, but then for now, a threshold value wouldn't use throughout the process. So throughout the whole building process, the split method simply split the samples along with features at a certain threshold, and then it's also recursively transverse the tree to make a prediction for one sample. Then with that, it also finds the most common class labels as well, a common class label that are found in a data set. Yeah, so that is for the decision tree algorithm. So the last thing that it does is that it simply tests the decision tree implementation by using the data set. I think I imported a particular data set. I think I use again, okay, the breast cancer data set again, and then split the data set into training and testing, and it fits the decision tree on the training set, makes predictions, and then finally it computes the accuracy. Yeah, and the accuracy was 0.91, which is about 91% or 90% accuracy. Yeah, and it's exactly 7. I think I'll pause here. If you have any question, we can go ahead and ask. So this a very quick and kind of fast and so quick. But then I encourage you. I've sent you about 4 links or so in your whole free time. You can check them out, and then see. And if you need more materials to understand it, you can also reach out to me. I'll suggest some videos and other things that just to aid more understanding. Yes, Benjamin. So I'll take.
Yes, actually, I was about to ask about that. Maybe your suggestions on some videos as well would help, and
Yes,
so that we can narrow down. You see, because we're not every week there's new things to learn. We can't. Difficult to know where to start from to begin to understand some of this. So maybe just to zero in on a few resources you could recommend strongly for us to start from as well would help.
yeah. So I'll suggest some videos to as well. Let me get it. Can I see these videos now?
So Prince, for the decisions tree, you can decide to split the data on two. So is it possible that the number can actually also be different, like 3 and more, depending on the data?
Come again. You mean can the number?
Can you split in 3 instead of 2 and 4 and so on and so forth, depending on the
Yeah,
data?
yeah. You can do those splitting using the decisions that we have. But the
Ah,
splitting is always from left, and right, left, right. So that.
okay, that's it.
So I let me check out for the materials. Benjani, I think I have to recheck these things again, and then I'll send them to you.
All right. Thanks.
Okay. So please, do you have any other question for me? If you have some questions, you can.
I think a Prince network has gone off. Or
Yes, guys. So thank you very much for joining the session, and I'll share the materials that you are requesting with you as soon as possible. If there are no further questions, I think I'll end the session here. And then if you have any question, you can feel free to inbox me directly. Okay. And Benjani, I think you can also try and then remind me if I don't send the documents by tomorrow.
All right. Okay. We'll do so.
Okay. So thank you very much, and please
Right.
enjoy the rest of your evening.
Sure. Thank you. Bye.
Thank you.
Sure, bye.